Greetings, everyone. My name is Paulo Joseph Trinidad Andaya, and I'm honored to present my final thesis report on superlearner model for fraud risk scoring, optimizing imbalanced data, and dynamic adaptation. In our modern hyper-connected financial ecosystem, the speed of innovation is matched by the speed of criminal adaptation. This research addresses the critical bottleneck in predictive analytics, which is the rapid decay of detection models when confronted with shifting fraud tactics. Over the next 20 minutes, I will demonstrate how our hierarchical self-healing ensemble architecture can maintain high effectiveness that can significantly reduce computational and operational costs associated with traditional model maintenance. To understand the necessity of this research, we must look at the economic trajectory of financial crime. In 2025, global spending on fraud prevention reached 21.1 billion, and that figure is projected to surge to 58.3 billion by 2030. This escalation is fueled by AI-powered attacks and synthetic identity theft that can bypass legacy rule-based engines. Furthermore, in the Philippines, the regulatory environment has moved from recommendation to mandate. The Financial Account Scamming Act, or AFASA, now requires regulated institutions to deploy real-time systems to safeguard consumers from scams and other fraudulent behavior. We are now at the point where the ability to adapt to threats in near real time is not just a competitive advantage, it is also a legal imperative. This research was conducted upon a rigorous analysis of the current state of fraud detection in banking and finance sector, especially in the advent of emerging technologies and markets. I would like to briefly discuss how these specific studies help build the foundation and basis for this thesis and derive my methodology. Future trends and predictions published by DataWalk in 2026 identified critical trend is the shift of toward modular tactical updates than full system overhauls. This directly inspired the frozen architecture layer of the proposed stack solution. In terms of regulatory scene, Hossein et al. Highlighted a compliance paradox where banks must detect fraud rigorously without blocking legitimate customers. This provided the direction to look at false positive rate or FPR as one of the key metrics in evaluating our model. The technical blueprint came from Springer Nature 2024, which established the groundwork for stacking ensembles, and Springer 2024 validated SMOTE as the gold standard for to address imbalanced data. Finally, IEEE 2023 provided the methodology for temporal segmentation, proving that tracking performance across time is the only way to truly capture concept drift. These articles collectively justify the need for a system that is modular, explainable, and chronologically aware. Our research centers on the dual challenge of fraud detection. First is class imbalance. Fraud typically accounts for less than 0.1% of transactions, often creating a needle in a haystack scenario where models develop a bias towards the majority class. This percentage should not be looked at as a small probability of transaction being fraud. Rather, we should look at it in terms of the affected individual and its impact. One fraudulent transaction out of 1,000 transactions can easily wipe out someone's hard-earned life savings, and the financial institution's inability to protect this one client can easily ripple out to loss of confidence from all other clients, not to mention heavy regulatory penalties. As such, that needle needs to be found. What makes it more challenging to find this needle is due to the second challenge, which is concept drift, where statistical properties of fraud are non-stationary. As fraudsters adapt, static models suffer a documented 37.4% ineffectiveness. Because traditional models are computationally expensive to retrain, There's a dangerous lag between emergence of new fraud tactics and the model's update, leaving institutions exposed to new fraud campaigns. To address these challenges, this research has laid out five primary objectives. First is to develop a computationally efficient adaptive model framework by designing a two-layer architecture using random forests, XGBoost, and MLP for deep pattern extraction, and then implement a lightweight adaptive meta-learner for tactical recalibration. We will then compare this framework against full retraining cycle and determine the speed gains and efficiency and also the operational stability of this framework. And then lastly, we will establish a operational boundary to prevent collapse in the decision making of the model. The significance of this study applies to three key stakeholders. For financial institutions, it offers a way to maintain high precision detection and keep up with non-stationary patterns and mitigate effects of concept drift. This also provides a framework to adjust to these changes and maintain classification of fraudulent transactions without fully retraining the whole ensemble models. This minimizes capital losses and operational friction in terms of trying to adapt to these fraud changes. For consumers, the focus is on false positive rate. By keeping false alarms low, we ensure the security does not come at the cost of poor user experience or account locks. For regulators, this architecture provides a verifiable methodology for model governance. And because of that, our adaptation happens in transparent meta layer, it is easier to audit how detection logic is being updated to meet emerging threats. Fraud detection has evolved through the years, starting with expert systems which are static, rule-based logic that were easy to interpret but impossible to scale to adapt to new trends. This gave way to supervised machine learning, specifically tree-based ensembles like random forests and XGBoost, which are excellent at handling nonlinear patterns. The current state now is stacking, where we blend unique expertise of different algorithms. This research breaks into the adaptive AI realm, where a model doesn't just detect, but it also learns how to learn from shifting environmental signals without human intervention. The framework was tested using European card transaction dataset from Kaggle. This is an industry standard benchmark containing nearly 300,000 transactions with a fraud incidence of less than 0.18%. To maintain cardholder privacy, features V1 to V28 or PCA transformed. To simulate real-world conditions, I applied chronological time split, 70% for training, 10% validation, and 20% for testing. This ensures that the model was always learning from past to predict the future. Perform the analysis of this research. I just use my local PC with the following specifications and relevant Python libraries for data processing and machine learning and data visualization. F1 score, ROCAUC, false positive rate were used as metrics to evaluate the model. Data preparation was a critical phase in this research. To solve the imbalance problem, I applied SMOKE, or synthetic minority oversampling technique, exclusively on the training dataset. By generating synthetic fraud instances, we ensure that the base learners receive strong enough signal to learn the specific decision boundaries that separate legitimate activity from sophisticated fraud anomalies. To manage high volume of records and memory-intensive nature of these stacking ensembles, all numerical features were downcasted from float 64 to float 32. Typically, especially in fraud analysis, raw data needs to be enhanced with features that will help uncover defining layer to identify fraud patterns or what we call a fraud fingerprint. For this research, two behavioral indicators were engineered. First is temporal cycles, which is derived from hour of day from timestamps to capture late night fraud spikes. Second is a sequential behavior where moving average of transaction amounts will help identify sudden deviation from the user's spending velocity. Finally, all features were standardized using standard scaler to prevent raw timestamps from biasing the neural network components of the ensemble model. Core of the superlearner is heterogeneous layer 1. For this research, three independent algorithms were used to capture a wide array of patterns. Random forest was used for its robustness in handling noisy transactional data. XGBoost was used for its efficiency in capturing complex nonlinear fraud signatures. Multi-layer perceptron or MLP was used for deep neural-based perspective on behavioral patterns. These models were frozen after initial training. By keeping these computationally expensive assets stable, we preserve the deep nature extraction capabilities while shifting the burden of adaptation to a much lighter layer with the use of logistic regression as layer 2 meta-learner. We will discuss this more in the next section. Another key point to note is that the evaluation and recalibration of the meta-learner was performed across time splits to simulate concept drift. Now, the breakthrough of this methodology is the modular update strategy. Traditional models require full rebuild to stay current, which is expensive and slow. Based on my own experience as fraud analyst, more often than not, by the time the model refresh completes, a new thread has started evolving. In the previous slide, we discussed about building layer 1 of base models. Layer 2 introduces the stack generalization layer, implemented via logistic regression. Instead of these models making a final classification, they pass their class prediction to this meta-learner to assign the respective weights in determining the final prediction. By keeping layer 1 frozen and making layer 2 adaptive, we can retrain only the lightweight meta-learner on very recent data slices. This creates a self-healing mechanism that can adjust its decision boundary in near real time or as soon as new fraud patterns are verified. To prevent data leakage, I use a stratified five-fold cross-validation approach to generate the input matrix. This ensures that the meta-learner is trained on out-of-sample predictions, allowing it to learn exactly which base learners to trust under different transactional conditions. As mentioned earlier, I simulated production environment by segmenting the testing set into five chronological splits, T1 through T5. Unlike a random split, this preserves a time-dependent nature of fraud, allowing us to observe how models decay as tactics move away from the initial training period. Establish a static baseline where weights were never updated to measure the natural performance decay that occurs when models are exposed to shifting tactics without intervention. The results demonstrate a powerful rescue effect. Both models started with a baseline F1 score of 0.77. As constant drift took hold, the static model's F1 score steadily eroded, reaching 0.63 by T4 and a low of 0.58 by T5. On the other hand, the adaptive model framework successfully recalibrated itself, maintaining a peak F1 score of zero point 0.8 during the drift periods. This represents a 26.7 improvement in reliability during T4, where static model posted its sharpest decline in terms of performance. This proves that a lightweight update can extract significantly more predictive value from existing models than static reconfiguration. Towards the end of T5 though, A crash in F1 score of the adaptive model was observed due to data sparsity sensitivity. More detail on this in the next sections. While F1 scores capture precise classification, the ROC-AUC measures the model's fundamental ranking ability. In this analysis, both models maintained an exceptional discriminative power, with scores above 0.95 across all time slices. This validates the vision versus decision hypothesis. The models can still see the fraud, still rank it higher than legitimate cases, but they lose the ability to draw a confident cutoff line. The adaptive layer fixes this decision by optimizing the classification threshold dynamically. From a business standpoint, the false positive rate is a very important metric. High FPR leads to legitimate accounts getting blocked and customer churn, not to mention the overall reputational damage for the organization. The findings show that while the static model's FPR quadrupled, reaching 0.0004 during the drift, the adaptive framework held a consistent FPR of 0.0001. By automatically reducing the influence of models that misinterpret new behavior as fraud, the meta-learner protects the legitimate user's experience. Again, we can observe that by T5, FPR of the adaptive model dropped to perfect zero. While zero false alarm is theoretically ideal, the collapse in F1 score, as shown earlier, presents the system's transition to a state of extreme caution, tagging nearly all transactions as not fraud. In terms of computational efficiency, a comparative review between the full retraining of the entire ensemble and the meta-learner update was performed. Full retraining took approximately 2 seconds. In contrast, updating the meta-learner took less than 0.17 seconds. This 11.9 operational speed up is a key finding for financial industry. This demonstrates that banks can modernize their defenses in near real time without taking primary systems offline for extensive, resource-heavy retraining cycles. Going back to the previous observation about the adaptive model and its performance collapse in T5, where the F1 score fell to zero due to data sparsity sensitivity. When fraud instances in an update window drop too low, or in this case reaching only less than 10 cases, the meta-learner lacks enough evidence to establish a stable decision boundary. This teaches us that adaptation is nonlinear. Future systems will require safety triggers to defer to static weights when signals are too sparse to support reliable update, ensuring systems remain active in low volume periods. The cornerstone of this research is the transition from rigid static defenses to near real-time adaptability. By utilizing a frozen base layer coupled with lightweight meta-learner, we have developed a modular architecture that drastically reduces technical debt and computational overhead. This allows financial institutions to efficiently pivot as fraud patterns evolve, maintaining high security standards without the need for massive hardware investments or frequent, expensive full retraining cycles. For organizations bound by established infrastructure, this framework offers a plug-and-play integration strategy. Institutions can treat their existing high-performing legacy models such as random forest or XGBoost as foundational base learners. By wrapping these models in a dynamic adaptive layer, the core logic remains untouched while the meta-learner handles environmental fluctuations externally. Furthermore, The choice of logistic regression as a meta learner addresses the critical industry need for explainable AI because the weights of the logistic model are mathematically transparent. Risk managers can provide clear, auditable justifications for why a transaction was declined. This meets the stringent transparency requirements set by modern financial regulators. Looking toward the next tier of defense, we propose the integration of unsupervised and isolation forests to detect zero-day fraud patterns that lack historical precedent. Additionally, exploring a Bayesian meta-learner will provide superior identity awareness, acting as a safety net to prevent performance crashes during the sparse data windows. Ultimately, this modular approach creates a resilient, low-maintenance ecosystem that balances computational efficiency with predictive agility. That's the end of my presentation. I hope you enjoy it as much as I did, and I'm looking forward to your feedback about my presentation. Have a good day.